All right. Are we ready to get started?
Yeah.
Fantastic. So we're trying to find the mass in grams of this many moles of oxygen. So they have something above to help us out. Let's kind of use that as a guide. So we always want to put the quantity we're given in the very first cell, in the very top left cell. We have this many moles. 3 sig figs after the decimal. And then we need the conversion factor. We're trying to go from moles into grams. What would be the conversion factor? We know we're going to need to have grams on top. We're going to need moles on the bottom. How do we figure out how many grams are in a mole of oxygen?
What did you say, sorry?
So how do we figure out how many grams are in a mole of oxygen gas? We're going to need the periodic table. There's a number that corresponds to the atomic mass, which is the molar mass. That would be 15.999. So I don't know if you would want us to maybe round that up to 16, but do you think they would prefer 16 or 15.999?
I guess 15.999.
All right. That is units, that's atomic mass units, which corresponds for this many grams in every 1 mole of oxygen gas. So mole cancels with moles. Now we just need to multiply together, and then we're going to do 15.999 times 0.950, and we get 15.19905. So let's see if we can match the sig figs. They have 1 before and then 3 after. We want to make sure ours matches. So we're going to have 1.599. And then we're going to need to make it times 10 to the first power, because we move the decimal place 1 to the left. And the units would be grams. And let me know when you're ready to continue.
Yeah, I'm ready.
How many atoms are in 1.05 moles of copper 1 carbonate? So we're going to need to find similar information to what we did last time. We're going to need the molecular weight of carbon 1 carbonate. So we're going to need the formula first. Carbon 1 carbonate, if I'm not mistaken, is CCU2O3, but I'm going to look it up real quick just to make sure. Copper 1 carbonate, yep. So this is the formula. So we're going to need to find the molecular weight of 1 carbon atom, molecular weight of 2 copper atoms, and then molecular weight of 3 oxygens. So do you have your periodic table open by chance?
No.
Do you possibly have one you might be able to pull out and use for this worksheet? Because we're going to need that. We're going to need the molar masses of these things. So we need.
Did you say like the molar mass of copper carbonate, right?
Yeah, we're going to need carbon first.
Yeah, I'm just like adding everything up. I have it like pulled up on my phone.
All right. So I just Googled it real quick. So carbon
I got like 123.55.
And then what would be the units for that?
Grams.
All right.
You
got 123.55?
Yeah.
That would be copper 2 carbonate. This one we just have copper 1 carbonate.
Oh, okay.
So I just Googled it, and then this one would have
187.1.
Yep, exactly. So how do we know if we want to put 187.1 on top or on the bottom of the conversion factor?
It would be on the top, right?
Yep, exactly. We want to have grams on top and moles on the bottom to make the units cancel. This many grams for every 1 mole of copper 1 carbonate. So mole on top cancels with mole on the bottom. And we're just going to multiply those together real quick. Or rather, my calculator is. $196.455. So they have one sig fig before the decimal and then 2 after. So we want to make it 1.96 times 10 to the second. So see if you can find the molar mass of potassium iodide.
1 second, sorry.
So this one is a little bit different. We're going to need to go from molecules to moles and then moles to grams. So we're going to have 2 conversion factors for this one. Potassium iodide is Ki.
I got 166.0028.
All right. So we're going to need Avogadro's number to help us convert molecules into moles. So that would be 6.02 times 10 to the 23 molecules in every 1 mole. And then what we need to do is we need to go from moles into grams. So we're going to have 1 mole on the bottom contains this many grams, 1.66. 0. Oh, sorry, messed that up. 166.0028.
Mhm.
Grams for every mole. So mole cancels with moles. Molecules cancel with molecules, and we have our answer in grams. So we're going to do 6.89 divided by 6.02. Can you tell me what that is real quick? 6.89 divided by 6.02.
What did you say, sorry?
So can you do 6.89 divided by 6.02 real quick?
Okay.
And then when you have that, multiply that by the molecular mass of potassium iodide.
Okay. Wait, what'd you get for grams? Oh,
That's what we're trying to figure out. We need to do.
I was just wondering like what you got. I just want to like.
Oh, I haven't done that yet. 6.89 divided by 6.02, and then multiply that by the molar mass. So 166.0028. I get 189.9932.
Yeah.
And then we have a 10 to the first because we have 10 to the 24th over 10 to the third over 10 to the 23rd. That gets us 10 to the first. And then we want to match the sig figs. So they have 1 before and then 2 after. We're going to make ours 1.90 times 10 to the third power because we already have 1 and then we're moving it 2 more places. So this many grams.
Okay, I got it.
All right. And then see if you can find the molecular mass of magnesium chromate.
I got 140.3.
Yep, perfect. So I want to see if you can fill in the conversion factor. Give it a try. You can write on the whiteboard.
So I just put like 140.3 grams like as like the denominator, and I put 1 mole as the numerator.
Yep, perfect. And then see what you get for your answer. All right, let me know when you have it, okay?
One second, I'm just like my phone is just glitching.
No problem.
Let me restart real quick.
No rush.
I got like a super long number. I got 2.9757. It's just like repeating.
I got something a little bit different. So I did the 250.9 divided by 140.3. I got 1.7883, and then we want to adjust that to match the sig fig. So we're going to make that into 178.8, and then we need to multiply that times 10 to the negative second. And we get moles.
Okay.
How many particles are in this many liters? So we're going to need to convert liters to moles and then moles into particles. So how many particles are there in a liter of ammonia, or how many moles are in a liter of ammonia gas? Do you have that sheet you had before that shows the rate?
No, I don't. 1 second.
Sorry, right?
You can search it out.
So a mole is equal to 22.4 liters.
Okay.
And then we want to convert liters, or sorry, I put that in the wrong space. 1.9 liters. And then we have the same conversion factor. And then a mole is equal to an Avogadro's number of particles. Mole cancels with moles. Liters cancel. So we're going to do 1.9 divided by 22.4, and then multiply that by 6.02. And we get 0.51. But then we want to make that, oh, hang on, it's 0.51 times 10 to the 23. So we're going to transform that into 5.1 times 10 to the 22nd. Particles.
Yeah, okay, got it.
Next, we have 1.24 liters. And then we're going to do 1 mole is equivalent to 22.4 liters. And then same thing as above. So we get 0.33325 times 10 to the 23 particles. I can't spell. And then we have, we're going to make it match the sig fig, so we're going to make it 3.33 times 10 to the 22nd.
Second. Yeah.
Yep.
Okay. 20 grams of phosphorus trioxide.
20 grams. There are 1,000 grams in every liter. So we're going to do 2,000 divided by 100, 20 divided by 1,000, which is the same as 2 divided by 100. And I'm too tired to do that right now in my head. That is 0.02 liters. So we're going to make that into 20 times 10 to the negative 3 liters.
One second, sorry.
Sorry, what was that?
No, I was just saying 1 second.
No problem.
Okay, I'm done.
All right. How many particles are in this many grams of ferric nitride? So we're going to do 1,000 grams in a liter. And then we're going to do 22.4 liters in a mole. We have 5.3 divided by 1,000 divided by 22.4. We get a really small number, 0.00023666, and then we want to match the sig fig. So we're going to move it 1, 2, 3, 4 decimal places. We're going to get 2.36. That's going to round up to 2.4 times 10 to the negative something. It's going to be 10 to the negative 1, 2, 3, 4.
I got it.
Oh, hang on. I think I forgot something. I did moles, but I didn't do the moles to particles. Sorry. I forgot that very last step.
Oh, yeah.
So grams cancels with grams, liters cancel. We're going to do 1 mole is 6.02 times 10 to the 23 particles. So I just need to multiply that answer by 6.02 times 10 to the 23. And then I get 0.001424. That's 357. And then we want to have one before and one after. So we're going to make this, oh, I forgot the 10 to the 23. So we're going to make it 1.4 times 10. We jump 1, 2, 3. 23 minus 3 is 20. So we get 1.4 times 10 to the 20 particles. That sounds more accurate.
Yeah, got it.
All right. My handwriting is really bad. I think I'm just going to type. So we're given a number of, oh, I wrote particles instead of grams. No, molecules is what we want. We want to figure out how many grams there are. So we want to go molecules to moles, and then moles to liters, and then liters to grams. So a mole is going to be 6.02 times 10 to the 23 particles. No, molecules, I meant to say. And then we have 22.4 liters in every 1 mole. And then we have 1,000, no, we have 1 liter is 1,000 grams. So let's make sure the units cancel first. Yep, we have grams as a result. So I'm going to multiply it. So for this one, I think I erased too much there. So I got 33,748.837 grams. And then we want to match the sig figs. So the 10 to the 23rd on top is going to cancel with the 10 to the 23rd on bottom. And then we want to make it 1 before and then 2 after. So we're going to make it 3.37. Hang on a second. And then we have to move the decimal place 1, 2, 3, 4 to the left. This many grams. All right.
I got it.
All right. How many particles are in this many liters of carbon tetrachloride? So we're going to do liters to moles first. 22.4 liters in every mole. And then we have a mole is equal to this many particles. So then units cancel, we're left with particles. Now we just have to do the math. I got this answer. And then we want to match the sig fig. So they have 1 before and then 4 after. So we're going to make ours 0.2016. Yeah, and that's it.
Okay, got it.
All right, so that's it for this page.
Yeah, I have this. Yeah.
All right. Sounds good. So we have to balance it first. How do we balance this? This is a combustion reaction. We can tell we have this reacting with oxygen producing carbon dioxide and water. So it's instantly, we know that's combustion. So how do we balance this combustion reaction? How do we start it off? Everyone has their own way of doing it. What I like to do is I like to start by making a list of everything I have. So on the right side, on the left side, I have 2 carbons. I have 6 hydrogens. And oxygen, it looks like I have 3. And then on the other side, we have 1 carbon and 2 hydrogens. Oh, no, just 1 carbon. My mistake. No, I had 1 carbon. I'm losing my mind. We have 1 carbon, 2 hydrogens, and then 3 oxygens. So we're going to need to triple the number of hydrogens on the right side. So now we have 6 hydrogens and 3 oxygens. Nope, we have 5 this time. 5 oxygens.
Yeah.
And then we have 1 carbon. No, hang on a second. Here, let me restart real quick. So I think we want to multiply this by 3. So now we have 5 oxygens. We have just 1 oxygen on, no, we have, I think we want to double this because now we have, no, sorry, I think we want to triple it. Now we have 3 oxygens plus 2 more. We have 5 oxygens. So we have 5 oxygens on both sides. Now let's make sure we have everything else we need. So we have 3 carbons on the left, 1 carbon on the right. So we're going to need to triple this carbon dioxide. So now we have, actually we want to make that 6. So now we have 6 carbons on both sides. But now we just modify the oxygen. So let's count all the oxygens we have. So on the left side, we have 3 plus 2. We have 5 oxygens. On the right, we have 12 plus 3. We have 15. So we have 3 oxygens plus an unknown number of O2 gets us a total of, this would be 15 altogether. So 15 minus 3 gets us 12. So this is going to have to be a 6 right here. Let's just make sure. And I like to put coefficients into boxes just because I get the O's confused with zeros sometimes, and I don't want that to happen. And that happens all the time. So this is going to be, whoa, I meant to make the box. 15 oxygens. So yep, we have 15 on both sides. So this thing is balanced. So we want to find the mole ratio of ethanol to carbon dioxide. So we put all the coefficients in terms of moles. So this is going to be 3 moles of ethanol, 1 mole of oxygen gas. Actually, it's 6. I forgot to put the 6 there. And then we have 6 moles of carbon dioxide and 3 moles of water. But actually, we can simplify this. We have 3s and 6s that have a greatest common factor of 3. So we can actually just make that into a 1 and a 2 and a 2 and a 1. Simplify that a little bit. So we have 1, 2, 2, and then 1. So the molar ratio of ethanol to carbon dioxide is going to be, ethanol is 1 and carbon dioxide is 2. And then the molar ratio of water to oxygen is going to be 1 to 2 as well. 1 water for every 2 oxygens. Makes sense?
Yeah, one second, I'm just writing it down. Yeah, I got it.
All right. Calculate how many moles of product would be produced by the complete conversion of 5 moles of the reactant in Voltprint. So we have to balance it first. So this one is pretty easy to balance. We have 2 oxygens, so we're going to need to double this and then double this as well. So now we have 2 of everything. It's balanced. Life is good. So we have 5.0 moles. So we're going to need a conversion factor here. Oh, how many moles of product? So we have this many moles of magnesium. So this is going to be 2 moles of magnesium for every 2 moles of product. So then 2 cancels with 2. Units cancel like that. So we just have 5 moles of product.
Instruments.
All right. So same thing, we're going to balance first. So we have 3 oxygens on the right, 2 on the left. We're going to want to make them both have 6 because that would be the LCM of 2 and 3. So we have 6 oxygens on both sides. We have 4 irons on the right. So we're going to put a 4 in front of the iron on the left. So now everything is perfectly balanced. So now what we need to do is do the conversion factor part. So we have 5 liters of the reactant in bold. That would be just O2. And then this would be, we could have the coefficient be any units. The last one was moles. This time we're going to make them liters. So this would be, in bold, we have O2 and then, the product. So the product would be 2 moles, no, 2 liters. Sorry, I keep getting mixed up. So 2 liters of, I think this is iron trioxide, iron 2 trioxide, if I'm not mistaken. And it would be 2 of those for every 3 liters of O2. Units cancel. So we're going to do 5 times 2 and then divide that by 3. So we get 3.33. I guess we would just make that 3.3 if we match the sig fig. So it would be this many liters of product.
Okay, I got it.
Perfect. So what do they mean by beautiful dimensional analysis? What's that part mean?
I don't know. 1 second.
You want to see if it's in your notes?
Yeah. The Canvas app on my phone isn't working for some reason. 1 second.
No problem. While you're doing that, I'll be right back, okay?
No problem.
I don't know anything about beautiful dimensional analysis, but I do know normal ordinary dimensional analysis. So I guess our only choice would just be to do it the normal way, I guess.
Yeah.
So we need to balance this first. And we're kind of running short on time, so I think I'm going to use a balancing calculator for this real quick.
Okay.
I'm going to cheat in the interest of time. So we have NH4Cl plus magnesium. I think this is magnesium sulfate. And then we get, I think that's ammonia, NH4, sulfate, magnesium chloride. So we get this for the balanced version. Yeah, that's it. And then what the number of moles of magnesium chloride produced by 25 grams. So the dimensional analysis is going to go like this. Of magnesium sulfate. And then we want magnesium chloride. So magnesium chloride is right there. Magnesium sulfate is there. So they have that 1-to-1 ratio. So it's going to be 1 mole. Oh, hang on a second. We're going to need to convert moles to grams to moles first. So magnesium sulfate has a molar mass of 120.3676 grams for every mole. So we're going to put 1 mole on top. We're going to put 120.3676 grams on the bottom. And then, then what do we do? So we have our answer in moles, and then we want to, it'll just be that 1-to-1 ratio. It'll be 1 mole of, what was this one? This one was magnesium chloride. All right, there we go. It's making a little more sense now. So I'm going to cancel things out. Grams with grams, moles with moles. So then we just need to do 25 grams divided by the molar mass. And I got 0.207697 moles of magnesium chloride, no, magnesium sulfate.
Or what'd you get, sorry?
Hang on, the units don't really match up here. Give me a second.
Okay, no problem.
Oh, I see what happened. So I just had the units wrong. So we want to make this here. I think I'm just gonna start over. So at the beginning, we have 25 grams magnesium sulfide. Yeah, and then sulfate. And then we have 1 mole of magnesium sulfate is equivalent to 120.3676 grams magnesium sulfate. And then on top, we have a 1-to-1 molar ratio. We can tell that they both have a coefficient of 1. So it would be 1 mole of magnesium chloride. Chloride is equivalent to 1 mole of magnesium sulfate. So now the units cancel properly. I don't know what I did before, but they didn't cancel right, but now they do. Yep, and then we have exactly the units we're looking for. So we had the number right, but I just messed up the unit. So we have, this is 0.20, but then I think we want to match what they have. We want to make it 20.77. Yep. And then that would be times 10 to the negative second. And the units would be moles of magnesium chloride.
Okay, got it.
All right. So how many moles of ammonium chloride are needed to produce 1.25 moles of ammonium sulfate? So start with that. And then ammonium sulfate. That one is the NH42SO4. So this one is ammonium sulfate. And then ammonium chloride is going to be this right here. Ammonium chloride and then this. So it's going to be pretty similar, except we have different molar ratios this time. It's not going to be 1-to-1 like last time. It's going to be 1-to-2, but the process is going to be the same. So we have this many moles of ammonium sulfate. And then we're trying to go, oh, this one is a lot easier. We're just trying to do moles to moles. We don't have to do grams to moles this time. So we have moles of ammonium sulfate on top. We want to have moles of a sodium. I can't talk today. Ammonium sulfate on the bottom as well. So we're going to make this. So we can tell from the balanced equation that it's going to be 2 moles of ammonium chloride for every 1 mole of ammonium sulfate. So we have 1 mole ammonium sulfate for every 2 moles of ammonium chloride. So we just have to, we'll cancel the units first. That cancels with that. And then we just have to multiply our given quantity by 2. So that's going to get us 2.5. Yeah, 2.5. And then we want to make sure we match the sig fig. So we're going to make that 2.500 moles of ammonium sulfate. No, sorry, ammonium chloride. All right.
Okay, got it.
Perfect. This is the last one then, number 4.
Yeah.
All right. I hope your teacher isn't disappointed with the lack of beautifulness in my work. It's pretty ugly.
It's fine, no problem.
Hope you don't get points off for that. So
It's fine.
calculate the number of moles of sodium metal needed to completely react with 6.55 grams of tin 4 nitrate to form sodium nitrate and tin metal. So we're going to need to write the equation ourselves. So sodium metal is just going to be Na. And then we have 6.55 grams of tin 4 nitrate. I don't remember the formula for that one. I'm going to look it up real quick. Tin 4 nitrate is going to be here. I think I'm just going to type everything because my handwriting gets bad sometimes. It's going to be just sodium, and then we have N4, and then O12, and then I'll just write the numbers later. And then they form sodium nitrate, and I don't remember that either. Sodium nitrate, let me look it up. That is just NaNO3. And then we have tin metal, which is just Sn. So sodium nitrate is NaNO3. And then tin 4 nitrate is N4. O12 SN. Okay. So we're going to have to balance this. And in the interest of time, I'm just going to cheat and use the calculator again.
No problem.
So we're going to get 4 to 1 to 4 to 1. So we want to do the dimensional analysis now that we have the equation. So we have 6.55 grams of tin 4 nitrate. And then tin 4 nitrate is the N4O12 thing. And then we want the number of moles of sodium. So we're going to need to convert grams of grams of tin 4 nitrate into moles of tin 4 nitrate. So the molar mass of tin 4 nitrate is going to be 366.73 grams per mole. We're going to put that quantity on the bottom. This many grams tin 4 nitrate for every 1 gram. No, for every 1 mole of tin 4 nitrate.
Yeah.
So we have the grams canceling with grams. We have moles left over, but now we want to take into account the molar ratios of these things. So calculate the number of moles of sodium metal. So sodium metal would be this first reactant. And then we have 6.55 grams of this thing right here. So they're both the reactants. We don't care about the products in this case. We only care about the reactants. So we're going to have 4 moles of sodium metal for every 1 mole of tin 4 nitrate. So we're going to make this, the 1 mole of tin 4 nitrate is going to go on the bottom. So every mole of tin 4 nitrate needs 4 moles of sodium metal. So let's just make sure the units cancel. So we have grams of tin 4 nitrate canceling with that on the bottom, and then we have moles of tin 4 nitrate canceling with the exact same thing, and then we're left with, oh, I forgot moles. Should be moles of sodium. I just put sodium. Oops. So let's just do the math real quick. We're going to do 6.55 divided by 366.73. And then we're going to multiply that number by 4. And I'll write it first, and then I'll adjust it to the right number of sig figs. So we get 0.071442205. That's probably enough. This is moles of sodium metal. So they have 1 sig fig before and then 2 after. So I think we want to make ours 7.14. And then this would be times 10 to the negative second, I think. Yeah. Moles of sodium metal. So this right here is our final answer, adjusted for the sig figs and everything.
Okay, thank you.
Yep, that's all. Yep. All right. Well, hopefully that was helpful.
Yeah, thank you. Have a good day.
You too. See you next time.